On November 5th, 2018, a spacecraft racing through the darkness 11 billion miles from Earth crossed a line that, according to some of the leading models at the time, was never supposed to be a line at all. Scientists had spent decades predicting a slow, gradual fade, a soft transition zone stretching for weeks as one environment gently gave way to another. Instead, the boundary hit almost instantly in under a single day, sharp enough to catch an entire generation of physicists off guard. That spacecraft was Voyager 2, and the boundary it crossed that day would go on to challenge one of the most basic assumptions ever made about where our solar system actually ends and the rest of the galaxy begins. To understand why this moment mattered so much, you first have to understand what that boundary actually is, and why nobody, even the scientists who spent their entire careers chasing it, was entirely sure it worked the way they thought. Our sun isn't just a source of light and heat. It's constantly exhaling, blasting a stream of charged particles outward in every direction at speeds that can reach over 1 million miles per hour. This outflow is called the solar wind, and it doesn't just fade away into nothing. It inflates an enormous invisible bubble around the entire solar system, a bubble scientists call the Heliosphere. Inside that bubble, the sun is in charge. Its wind, its magnetic field, its rhythms shape the environment for billions of miles in every direction, engulfing not just the planets, but vast stretches of empty space well beyond the orbit of Neptune and Pluto. But that bubble isn't infinite. Eventually, the pressure of the solar wind weakens enough that it can no longer push back against the material drifting between the stars, the interstellar medium, and somewhere out there, the two forces meet. That meeting, point, that outer skin of the sun's bubble, is called the heliopause. Cross it, and you have left the direct influence of our own star behind entirely. You are, for the first time, in the space between stars. For most of the 20th century, this was little more than theory. Nobody had ever measured it directly. Nobody even agreed on how far away it was. When the Voyager mission was first proposed back in the 1970s, some scientists genuinely believed the edge of the solar system might sit just bay, on the orbit of Jupiter, a few 100 million miles from the sun. It sounds almost quaint now, but at the time, the scale of the heliosphere was one of the biggest open questions in all of astronomy. Nobody had a spacecraft that had ever gotten far enough away to check. That uncertainty is part of what makes what happened next so remarkable. Voyager 1, remember, had already been drifting outward for decades, and in August of 2012, something changed. Instruments detected a sudden drop in particles streaming from the sun and a corresponding jump in particles arriving from deep space, the telltale signs that it had likely crossed into a new environment entirely. But there was a problem, one that would end up aping the entire scientific debate for years afterward. Voyager 1's plasma science instrument, the one tool capable of directly measuring the density and temperature of the material surrounding the spacecraft, had stopped working decades earlier, aged not long after its Saturn flyby. Without it, scientists were left trying to prove Voyager 1 had truly left the solar system using nothing but indirect clues, fragments of evidence pieced together like detectives working a case with half the crime scene missing. The clue that finally settled it, for most researchers anyway, came from a burst of solar activity that had erupted from the sun months earlier. When that shock wave eventually caught up with Voyager 1, it caused the surrounding plasma to oscillate. And because plasma made of dense, interstellar material vibrates at a different frequency than plasma from the thinner solar wind. That oscillation acted almost like an echo, a kind of sonar ping, bouncing back information about the density of the material around the spacecraft. Using that frequency, physicists were able to calculate backward and pinpoint the actual date Voyager 1 had crossed into interstellar space, a moment that had already happened more than a year before anyone confirmed it. But not everyone was convinced. Some researchers argued the data didn't line up as cleanly as it needed to. There was no sharp, obvious jump in the magnetic field, the kind of dramatic shift many models predicted should mark a true crossing from one region to another. Instead, there was only a gradual, almost sluggish transformation, stretchy, hung out over nearly a full month, so slow and blurred at the edges that entire papers were published debating whether Voyager 1 had truly broken through, or whether it was still lingering in some strange, undefined in-between zone that didn't match any tidy textbook diagram. Even the mission's own scientists later admitted this crossing looked messy, chaotic, nothing like the clean line they had been expecting for 50 years. That lingering uncertainty is exactly why Voyager 2 mattered so much when its turn finally came 6 years later. Unlike its twin, Voyager 2's plasma instrument was still fully functional, meaning that for the first time, scientists wouldn't have to reconstruct the crossing from a distance using second-hand clues and clever inference. They would be able to watch it happen directly, in real time, with hard numbers instead of educated guesses. And what they saw stunned them. Where Voyager 1 had drifted through a slow, ambiguous transition lasting the better part of a month, Voyager 2 shot through its own crossing in less than a single day. The solar wind particles around it plunged suddenly. The density of surrounding plasma spiked. Cosmic rays from deep space flooded in. It was fast, clean, and almost shockingly decisive, the exact opposite of what its twin had experienced years earlier. Researchers studying the region even gave it a nickname that stuck. They called it Voyager 2's clean break from the solar system, a phrase that captured just how different this crossing felt compared to the murky, drawn-out departure of Voyager 1. That difference alone reopened questions nobody had fully answered. If both spacecraft were leaving the exact same solar system, passing through the exact same fundamental boundary, why did one experience a sudden sharp wall while the other drifted through something closer to fog? Part of the answer came from something Voyager 1 had passed through that Voyager 2 simply didn't. Just before its final crossing, Voyager 1 spent time inside what scientists came to call a stagnation region, a strange pocket roughly 8.5 astronomy, ICAL units wide, where the outward flow of solar wind plasma essentially stopped completely. The plasma wasn't accelerating away from the sun anymore. It was, in the words of one researcher who studied the data, essentially just sitting there, trapped, motionless, piling up against some invisible resistance before the spacecraft finally broke through into true interstellar space beyond it. Voyager 2 never encountered anything like that. Instead of a slow-motion stall, it passed through what scientists labeled a transition region, followed by a distinct boundary layer where incoming cosmic ray particles increased sharply, and then, almost immediately after, the clean break itself. One researcher who compared the TAB WOE crossings put it plainly. Voyager 1's departure looked messy, while Voyager 2's looked almost surgical by comparison. Same boundary, same solar system, two completely different experiences recorded by two nearly identical spacecraft passing through it years apart. And that wasn't even the strangest part. Here is where the story of a boundary that scientists said shouldn't behave the way it did really begins. Because the heliosphere isn't static. It breathes, expanding and contracting slightly as the sun cycles through roughly 11 years of rising and falling activity, a rhythm scientists have observed for generations. When solar activity increases, the pressure of the solar wind should push the heliopause farther outward, inflating the bubble like a lung filling with air. When solar activity quiets down, that same bubble should relax and pull back inward slightly, deflating just a bit. Voyager 1 crossed the heliopause in 2012, during a period of unusually high solar activity. Voyager 2 crossed it 6 years later in 2018, during a period of notably lower solar activity. According to the models, according to the lung-breathing logic scientists had relied on for decades, these two crossings should have happened at meaningfully different distances from the sun. They didn't. Voyager 1 crossed at roughly 121.5 astronomical units from the sun. Voyager 2 crossed at almost exactly the same distance, around 119 astronomical units, a gap OF barely 2.5 astronomical units, despite crossing years apart from different directions during opposite phases of the solar cycle. One of the mission's veteran scientists, a physicist who had worked on the project for decades, put the confusion bluntly. Taking the models at face value, researchers had genuinely expected a noticeable difference. Instead, they got what amounted to a coincidence nobody could fully explain, one that suggested the outer skin of our solar system might be far stiffer, more stable, or more strangely synchronized than any existing model predicted. It was as if the boundary that was supposed to breathe in and out with the sun's mood swings had, at least in these two specific locations, simply refused to move the way it was told to. Then came the magnetic field, and this is where the idea of a boundary that scientists said shouldn't exist really starts to take shape. For decades, the working assumption was straightforward. Inside the heliosphere, the magnetic field is generated by the sun and carried outward by the solar wind, stretching across the entire bubble in a specific, predictable orientation. Outside the heliosphere, in true interstellar space, the magnetic field comes from an entirely different source, shaped by the ambient, material drifting between the stars for light years in every direction. These are, in theory, two completely separate magnetic systems with no reason to line up. Cross from one into the other, and the direction of the magnetic field should shift, often dramatically, marking an unmistakable signature that you have truly left one regime and entered another. That is not what either spacecraft found. When Voyager 1 crossed the heliopause in 2012, researchers watching the data expected to see a distinct jump in the direction of the magnetic field, the kind of unmistakable signal that would settle any doubt once and for all. It never came. The field's direction barely shifted at all. Some scientists, understandably skeptical, wondered if this meant Voyager 1 hadn't actually left the heliosphere at all, since the missing magnetic signature was exactly the kind of evidence a true crossing was supposed to produce. Then, 6 years later, Voyager 2 crossed the very same kind of boundary in a completely different location, under different solar conditions, using an entirely different data set. And the exact same thing happened again. Almost no change in the magnetic field direction whatsoever. One of the lead researchers analyzing the crossing described it as one of the most genuinely puzzling results the mission had ever produced. Whatever was creating the interstellar magnetic field beyond the heliopause, it appeared to be strangely, almost impossibly aligned with the magnetic field generated by our own sun millions of miles away, as if some larger, unseen structure was linking two regions of space that were never supposed to be connected at all. This is the boundary scientists said didn't exist, at least not in the form textbooks had described for half a century. Not a hard, absolute wall separating two disconnected magnetic universes, but something far stranger. A threshold where particle density spikes almost instantly, where cosmic rays flood in and solar wind particles vanish within hours, and yet where the underlying magnetic architecture of space seems to slide almost seamlessly from one side to the other without so much as announcing the change. It behaves like a sharp line and a blurred smear at the very same time, depending on which instrument you're reading. And the strangeness didn't stop there. Voyager 2's fully functioning plasma instrument allowed scientists to measure something Voyager 1 never could, the actual temperature of the material on both sides of the boundary. What they found was that the plasma just outside the heliosphere, out in true interstellar space, was colder than the plasma inside the bubble, exactly as researchers had predicted based on theory. But it was also far hotter in absolute terms than anyone expected for something drifting so far from any star, registering temperatures north of 50,000 degrees Fahrenheit. That number sounds almost absurd for a region of space so empty and calm. The explanation lies in just how thin and diffuse the material actually is out there. There are so few particles per cubic inch that even though each individual particle carries enormous energy, there simply isn't enough material present to transfer meaningful heat to anything nearby. A spacecraft could sit in 50,000 degree plasma and remain, for all practical purposes, in a deep freeze, because temperature in a near vacuum behaves nothing like temperature in the world we're used to. Voyager 2 also confirmed something else that reshaped how scientists talk about this boundary altogether, something that undercuts the very idea of it being a clean, sealed wall at all. Researchers began describing the heliopause as a leaky border, and they meant that literally in both directions. High-energy cosmic rays from deep interstellar space don't stop cleanly at the heliopause and wait for a spacecraft to formally declare a crossing. They bleed inward, seeping through the boundary and gradually increasing in intensity for millions of miles before a spacecraft ever reaches the so-called official edge. And the same leakiness works in reverse. Material born inside the heliosphere, particles carried outward by the solar wind for decades, doesn't stop dead at the boundary either. Some of it slips outward into interstellar space, blurring the line between what belongs to our sun's bubble and what belongs to the wider galaxy. The heliopause, in other words, isn't a sealed membrane. It's something closer to a porous, breathing skin, letting material seep through in both directions, long before or after the moment any spacecraft instrument declares an official, tidy crossing. Put all of that together, and you start to see why this moment genuinely upended expectations that had stood for decades. Scientists had spent nearly 50 years imagining the heliopause as something close to a hard shell, a rigid boundary layer that would expand and contract predictably with the solar cycle, separate too magnetically. Distinct halves of space with a decisive signature and mark a location where the influence of our sun simply, cleanly stopped. Voyager 2 showed that almost none of that holds up cleanly under real measurement. The distance barely shifted with solar activity when it should have. The magnetic field barely rotated when it should have jumped. The particles leaked through in both directions long before or after any official crossing. And the character of the crossing itself looked completely different depending on which spacecraft, which location, and which moment in the solar cycle happened to be involved. It is a boundary, and it is real. Cosmic rays and solar wind particles genuinely do change dramatically across it, but it does not behave like the crisp, well-defined wall a half-century of theoretical modeling insisted it should be. There's a deeper reason all of this matters beyond simple curiosity about where our solar system technically ends. The heliosphere isn't just a boundary line drawn in empty space. It functions as a shield, deflecting a significant portion of the galaxy's most dangerous radiation, high-energy cosmic rays that can damage biological tissue and complicate long-duration space travel. Understanding exactly how that shield behaves, how porous it really is, how it responds to the sun's changing moods, and how consistent or inconsistent its boundary truly is has real consequences for how scientists think about protecting future astronauts on deep space missions, and even for how they think about the conditions necessary for life to exist and persist on worlds orbiting other stars, each presumably wrapped in a bubble of their own with its own porous, leaky edge. That is part of why NASA didn't stop chasing this mystery after Voyager 2 crossed over. In September of 2025, a new spacecraft called the Interstellar Mapping and Acceleration. Probe launched from Kennedy Space Center, designed from the ground up to pick up exactly where the Voyagers left off. Rather than flying all the way out to the boundary itself, a journey that took the Voyagers decades to complete, this new mission takes a different approach entirely. Positioned roughly 1 million miles from Earth, it uses a suite of 10 specialized instruments to detect what are known as energetic neutral atoms, strange, uncharged particles created when a fast-moving charged ion collides with a slow neutral atom drifting through space. Because these particles carry no electric charge, they aren't dragged along by magnetic fields the way charged particles are. They travel in straight, undisturbed lines all the way from the distant edge of the Heliosphere back to instruments stationed near Earth, allowing scientists to reconstruct a map of that far-off boundary without ever having to physically travel there. In a sense, this new mission is using light from a place we've barely touched, tracing the shape and texture of the Heliosphere's outer skin the way astronomers once mapped distant nebulae, using nothing but the photons that happened to reach their telescopes. That approach builds directly on an earlier discovery made by one of this new mission's predecessors, an older spacecraft that first noticed something scientists nicknamed the ribbon, a narrow, unexpectedly bright arc of these same energetic particles stretching across a portion of the sky, a feature nobody had predicted and nobody fully understands even now. Nearby, researchers also identified something called the belt, a broader, more diffuse band of similar activity. Both features sit right at the edge of the heliosphere, in the very same porous, leaky, magnetically confused region the two Voyagers physically passed through years earlier. And both remain active subjects of ongoing research precisely because nothing about that boundary has turned out to be as simple as the old models predicted. It's worth pausing here to appreciate just how strange it is that humanity's best data about the true edge of our solar system still comes primarily from two aging machines built with technology from the 1970s. Spacecraft, with computers less powerful than a basic calculator, still transmitting data back to Earth at a rate slower than an old dial-up Interno. T-connection. Every single one of these boundary mysteries, the mismatched crossing distances, the missing magnetic field rotation, the leaky border, the stagnation region. Voyager 1 got trapped and that Voyager 2 somehow avoided entirely. All of it comes from instruments older than most of the scientists currently analyzing the results. And yet this ancient hardware managed to identify contradictions serious enough to send an entire new, purpose-built 10-instrument spacecraft chasing after answers nearly 50 years after the original mission first launched. It's also worth understanding just how differently the two Voyager teams had to work in order to even reach these conclusions in the first place, because the contrast says almost as much about the boundary as the data itself does. When Voyager 1 approached its crossing back in 2012, mission scientists were essentially flying blind on the single, most important measurement they needed. Without a working plasma instrument, they had no direct way to measure the density or speed of the material surrounding the spacecraft, the exact numbers that would tell them, beyond doubt, whether they had truly left the sun's influence behind. Instead, they had to rely on indirect detective work, waiting for a fortunate coincidence, a burst of solar activity that happened to catch up with the spacecraft months later and caused the surrounding plasma to ring like a bell. That ringing gave them a frequency, and that frequency gave them a density, and that density finally let them calculate after the fact when the true crossing had actually happened. It was clever, resourceful science, but it was also fundamentally reactive, dependent on lucky timing rather than direct observation. Voyager 2 never had to rely on that kind of workaround. Because its plasma instrument had survived intact, scientists could watch the crossing unfold moment by moment, density rising, temperature shifting, solar wind particles vanishing, all recorded directly rather than reconstructed after the fact. That is part of why researchers describe Voyager 2's data as so valuable, even though it arrived 6 years after its twin's dramatic milestone. It wasn't just a second data point confirming what Voyager 1 had already shown. It was, in many ways, the first true, direct, fully instrumented measurement of what crossing this boundary actually looks like in real time. Everything scientists thought they understood about the heliopause before November of 2018 rested on incomplete evidence and careful inference. Everything they've learned since rests on hard, direct measurement, and that shift in evidence quality is exactly why so many of the old assumptions started falling apart the moment real numbers replaced educated guesses. There's another piece of this story that rarely gets the attention it deserves, and it involves the stagnation region Voyager 1 passed through before its own crossing, the strange pocket of space where the solar wind essentially stopped moving altogether. Scientists still don't fully understand why that region existed, why it stretched across roughly 8.5 astronomical units, or why Voyager 2 apparently sailed past that same general area of the boundary without encountering anything similar. One leading idea suggests the shape of the heliosphere isn't a smooth, symmetrical bubble at all, but something closer to a windsock, stretched and distorted by the sun's own motion as it drags its bubble through the surrounding interstellar medium, creating thicker, more turbulent regions in some directions and thinner, cleaner regions in others. If that's true, then the very idea of a single universal heliopause distance becomes almost meaningless. There wouldn't be one edge to the solar system. There would be many, all slightly different, depending on which direction you happened to be traveling in when you finally broke through.